Hi, in this video, we're going to talk about a somewhat clever way of building a heap with initial data. So as you've seen in a number of tests, in order to create a heap with data, we first just instantiate an instance of the min heap, and then we insert the data from a list one by one, right? So it would actually be very convenient if in the initializer of the min heap that it takes a optional parameter with the list of data that optional meaning by default it can be none, so we'll start with an empty heap. But if the initial data has a list of things in it, then we just insert those data into the heap as part of the initialization process. Now, since we've done this before in our test, it would be very tempting to just write the initializer with initial data by just kind of inserting all the data from initial data and one by one, and like we did in the test, and then be done with it. And that's in fact what the original author of binary heap, Williams, did back in the days. Now, interestingly, there's actually a very simple and very elegant implementation that's slightly different, and it's also faster than what a naive implementation would do. And that would be using the percolate down method that we wrote. It's actually invented by a different computer scientist named Floyd, and this is the source if you want to look at what he did originally. And this process is often just called building a heap or heapify. Now in the readings it's called order heap, so we'll just continue with that terminology here. Now for this process, I'll actually take the opposite approach from what we usually do. I'll actually show you the code first because it's so simple, and then I'll explain how it works. So the dunder init, now it takes an optional initial data. If the initial data is none, then we did what we do before, is just to create a simple array with the first with the element in the index 0 to be none, right? Now, if the initial data is not none, then what we're going to put in the heap or the array that represents the heap is, well, the element at index 0 is still none, right? We always have that. And then we just concatenate the list of none with the initial list of data. Now, we have to point out, it's very important that what we do here is that this list concatenation, it creates a new list that is the concatenation of these two things, right? Now we're not making a deep copy of all the data that is in the list, right? This new list, it just contains the references to all the elements in the list of the initial data. Okay, so this is just a shadow copy, and I also want to point out here, I think in the readings the code was to make a deep copy, and I don't think that's correct, although I'll have to confirm it with the original author of the reading. Okay, and then once we put everything in this in our array that represent the heap, well, the shape property we have to think about, because this is a heap, so we must think about the two properties, right? Is the shape property satisfied? Well, it is, right? Because as we already saw, the shape property really just says it's the array, the data, the elements in the array must be just contiguous with the first one being none. So that shape property is satisfied. Now, what about the heap property? Well, the chance is the things in the initial data is all kind of random, so it's highly unlikely that they will satisfy the heap property. So that's what we'll have to fix, and we'll fix it by calling method order heap. And what the order heap does is deceptively simple. So we start in the middle of the heap. So this is the length of the entire heap. We divide it by 2, so we start somewhere in the middle, and then we go backwards. That's what the range minus 1 is, right? And we go all the way back to 0, but not quite 0, right? Because the end index is exclusive. So we don't go all the way back to 0. 0 has the none. We actually go all the way back to 1 and including 1. And we just call the percolating down starting at that number. So we start in the middle, we go back 1, percolating down from there, go back 2, percolating down from there, all the way to the the first element of the tree, or the root of the tree. So that's it, 2 lines of code. So to most of us, the way the code is written, it's probably not immediately clear why or how it works. So let's look at an example. So let's initialize the min heap with this series of number, and remember, this is just in an array, right? So this is, if we draw it out in the binary tree form, that's what it looks like, 593, so 593, and then 7112A, 7112A. Okay, so this clearly does not satisfy the heap property, right? So for example, 9 is greater than 1, 5 is greater than 3. So this is completely in the wrong order. So what the algorithm tells us to do is that we'll start at the element at index size of the heap, which is 7 divided by 2, integer division, so that gives us 3. So 1, 2, 3, right? So we started there and we're percolating 3 down. Okay, now in this subtree here, there's nothing to do here because it already satisfied the heap property. So we move on to the next one. We move backwards, right? So this is at index 3, and then now we are at index 2. And in index 2, now the number 9, we do the percolating down here. We'll have to swap 1 and 9, right? So we bring 1 up and we percolate 9 down. Okay, now this subtree will satisfy the heap property. So we move backwards because we were percolating down at index 2. Now we should percolate down at index 1, which is 5. Okay, and in this case, we percolate down, and we should already know this. This is 5. 5 is greater than the smaller child of 1, so we'll swap these two, right? And then we try again. 5, look at the smaller child of the 2, which is 7, and 5 is already smaller than 7, and we are done. So this is good. And when you check this tree, well, we're done because we were percolating down the root. So there's nothing else above the root, so we're done. Now, if we check the entire tree, the whole tree has satisfied the heap property. So great, we started with kind of a mess, and we ended up with a min heap. So hopefully you see how that works, and now it's your turn. This is I'm going to ask you to try to initialize a min heap with these numbers. They almost look like the previous example, except it's not quite the same. And it should give you an interesting exercise once you kind of go through the process that we went through earlier. So if you want to verify your result, here it goes. This is the initial tree that clearly does not satisfy the heap property. And so we start at the size of the tree, 6 divided by 2. We start at index 3, and we try to do the percolating down here. Well, nothing needs to be done here. So we move backwards the element at index 2. Now this clearly does not satisfy the heap property, so we'll stop 1 and 9. So we come to here. Once we're done here, we'll move up from index 2 to index 1. And again, this clearly does not satisfy the heap property, so we stop 15 and 1. But 15 is not done though. 15 is still bigger than its 2 children, so we further percolate 15 down to the smaller child, which is 7. And we're done here. So now this entire tree is a min heap. And if you want a more complex example, you can go to our favorite visualization tool here, and there's a build heap button here that it show you a nice animation of how it generates a random kind of heap and show you a nice animation of how this process actually works. I'm not going to complete the animation here. You can try it on your own. And as is customary, that once we have some code, we would like to test it. The test here is nothing clever, so we'll just start with the data that from the examples that we worked out earlier, and then we initialize a min heap with that data, and then we know what we expect once the min heap, the order heap process is done, and this is what we expect the heap to contain. We make sure it's equal, and then we make sure the size is correct. So that's it for the test. Now the more important thing is, now that we see the code, we walk through it and see how it works. So how does it actually work, and why does it work? So let's first think about what percolate down really did. So the assumption of percolate down is that only the root of the subtree that starts at the starting index is out of order, right? Remember when we wrote this, we move, it's for remove, and we move the last element from the heap to the root of the element, right? So that root is potentially out of order, but everything else in the heap is still in the heap order. So percolate down would work if both child subtree satisfy the heap property, and we only need to move the root of the subtree. Okay, so that's the assumption. Now, then the next thing is, why are we starting at length of the heap divided by 2? Well, because we want to start at the second lowest level. And the second lowest level is kind of where the heap property might not be satisfied, right? Because when you think about it, the lowest level, each subtree only has a single node, and those subtrees will always satisfy the heap property. So the second level is where things may not work as far as the heap property, the heap order is concerned. So we call percolate down on all the subtrees that start at the second lowest level, turn all of them into a min heap, and then once we're done with the second level, we go up one level now, because the level above it, or the subtrees that starts at these nodes above the second lowest level, they might not satisfy the heap property, even though their child subtrees all do. So again, we'll call percolate down on this level, and we just kind of repeat the process, keep going up the tree, and until we get to the root. And in that case, once we get to the root, we should be confident that the entire subtree, the entire min heap do satisfy the heap property. So hopefully that makes sense, and if not, think through it again, and if still not, please do ask questions in the discussion forum. So the next question is, what is the performance of building the heap with this approach? So this approach uses percolate down a lot, and we've discussed earlier, percolate down is out of log of n, and the number of times that we call it is about half as many times as their number of elements in the heap. So 1/2 of n is, in the world of big O, it's basically just out of n. And when you put these together, you would expect the performance is out of n log n. Okay, and that is no better than the naive implementation, in which we simply use insert to insert all the data into the heap. However, if you remember that we make the claim at the beginning that building the heap this way is actually faster than the naive implementation. And as a matter of fact, the performance of building the heap this way is not n of log n, but it is just O of n. It's linear. If you want to read about a proof, the readings actually contains the entire very rigorous proof. It's an optional topic, but if you have time and are interested, it's a fun topic that you can read about. More importantly, I think we should at least have the intuition why instead of being O of n log n, this is O of n. So when you think about it, that even though percolate down is O of log n, but where it is invoked and the number of times that it is invoked, well, it is actually invoked many more times when it's lower in the tree. Okay, so think about the tree. When we first started, we invoke it in the second lowest level, right? Now all the subtrees in the second lowest level is only height of 1. So percolate down, really for all those subtrees, it has to do at most 1 swap. And right there, that's half of the number of times that percolate down is called. So, and then when you move up 1 level to the, let's say, the third lowest level, well, the third lowest level, the height of all those subtrees, they're just 2, and so it just takes at most 2 swaps that percolate down would have to do. And the number of times that percolate down has to be called in the third lowest level is half as many times as the second lowest level. So even though it does more work per percolate down, but the number of times that it's called is already half. So when you kind of repeat this process, when it gets to the root of the tree, yeah, it takes longer to percolate the element at the root of the tree down to the bottom, but it's only called 1 time. So so this is actually what gives it the speed. When you compare this to the naive approach in which insert is used, remember insert uses percolate up, and percolate up, it always takes the last element and potentially move it all the way to the position of the first element in the heap. Now, even though the tree, when it starts, it's small, but over time it grows and it can grow pretty big. And in such case, it percolate up always has to traverse the entire tree, or at least the entire height of the tree. There's no, just moving things partially through the tree like what percolate down can do. So that's why using insert and using percolate up is more costly than doing percolate down.